Okay. Because I've got some data to show you as well, so let me do the document cam here. So, I didn't bring the book. Actually, I tend to cut pages out of the book. This is like a book I cut out. Like, why do I want to bring the whole book when I want to show 3 pages? You know what I mean? So I tend to do that. And I wanted to show you this data because it brings up a couple points. Let me see if I can hone in on that a little bit and make it a little darker. So, lights are all, I guess you can get them halfway. Okay, we'll just leave it like that. Okay, so up on top it says radiation absorptivity. That means how much of the solar radiation, you see that title, is absorbed. And if it was 1.0, that means all of it. So you can see there's no 1.0, but if you look here, and this is actually bigger up here, white cattle tend to absorb half of the solar radiation that comes onto them, okay? But if you get darker, red, 0.8, and then like an Angus, that's 0.9. That's pretty good. Only 10% is reflected. And you can see how, we talked about this last week, white is the best color for absorption. Is the worst color for absorption, and black is the best, and that data shows you for cattle, pigs. It varies a little bit with the fleece because a weathered fleece would be darker. And the darker you are, the more solar radiation you get absorbed. So like, look at the soil. Dark soil, 0.95, that's pretty good. Grass, 0.7, concrete, 0.85. But then look at the other column, infrared radiation. Now this is, stuff that we can't see except my thermal gun can see it, right? Do you see how infrared radiation is colorblind? Put that in your notes. I mean, color doesn't make any difference to an infrared heater, because you can buy an infrared heater. And basically, an infrared heater is colorblind. But color has a big factor to play in solar radiation. Okay? So that's one thing to get the point of. And then, let's see, what else do I have here? Which one is this? Okay. This one says thermal conductivity. So, I'll never ask you those units, but the point is, still air is what, 0.00059. A very low number, which means it's a good insulator. And that value is given on the far right column, insulator value. So air, still air, notice that? How they even said still air is a great insulator. So when you have double pane windows, what's between it a lot of times? Air. Or I think they even, in some cases, put argon between there. That's even a little better insulator. But then look at wood, conducts a little more. Still water, notice it has to be still. Because if it's not still, then you can't talk about conduction. You have to talk about what heat transfer mechanism. Convection, if it's moving. Anyway, you can see there. Then aluminum is a pretty good conductor. 0.5, relative to air. I mean, that's many hundred times better than air. Okay, so that's that. That's 2 data points I want to make. And then I want to draw something here. So let me get back. Okay, so now I'm going to draw the thermal neutral zone, and the x-axis is ambient temperature. Which higher goes off to the right, okay? Ambient temperature. Make that a B. I don't know if you ever noticed last week, do you know there was no values ever? Because it depends on who you're talking about. The milking dairy cow, the baby pig, Artemis up here. It depends on who you're talking about. Draft horse, race horse, pregnant animal, a male, whatever. And so I'm going to give you some values in a bit. But remember, LCT is here, and I'm going to abbreviate. UCT is there, and that defines the thermal neutral zone. But now watch what I'm going to do. I'm going to watch that data point all the way up here. Because now I'm going to put another graph on top of this graph. So this is a new twist, which none of the charts we saw last week did this. What I'm going to do now is label the y-axis. I have the same x-axis for both graphs, but the y-axis will be different. So you remember this is like, let's say, heat production. Right? You could call it metabolic rate. What was the lowest amount of heat produced? Basal metabolic rate. So right there I could go BMR. And, okay, so you know in the thermal neutral zone, that's about this value right here. Artemis, taking a break? Good. Let me put that data in blue. Okay. Now, on the upper graph, I want to monitor body temperature. I'm going to do that over here. Body temperature of the animal we're talking about. And now we're talking about any animal, so not any specific animal. But then I want to do two more vertical lines. Remember how the one graph called it the survival zone? Zone of survival. So if this is the thermal neutral zone, the far left and far right vertical lines give us the survival zone. Okay? And then you could call this the absolute lower critical temperature, the absolute upper critical temperature. Did you get that? Yeah. Okay. This is kind of a review of last week, but adding some more data. So you know if it gets colder than LCT, and that's actually the most, the easiest value to figure for an animal, because you can put an animal in an environmental chamber and crank down the temperature and monitor how much carbon dioxide they're making. And as soon as metabolism increases, they're going to start making more carbon dioxide. So that's how they do that in an environmental chamber. So in a little bit, I'm going to show you data, actual for animals that have LCTs given, okay? But you know heat production goes up to the left of LCT, right? Correct, I should say? So let's go like this. And what's this point called? I've maxed out my heat production. What was that called? What was it? Well, you develop hypothermia past that line, but the metabolic rate is called summit metabolism. Okay? Okay, summit metabolism. You can't make any more heat, and hence, to the left of that line, tissue starts freezing. And that's death. Someplace there. Death by hypothermia, right? Correct? Then on over here, when you get warmer than the upper critical temperature, it'd be nice to even keep the same temperature, or the same heat production, right? But you can't. If the dog starts panting, that makes more heat. Although you're going to lose heat, you're going to have some kind of increase here. And then notice what happened. Well, yeah, okay. So then after tissue becomes so hot, it starts dying. So look at that. Down, death. Okay, now let's do the upper graph. Body temperature in the thermal neutral zone stays in a range. Now, over on the y-axis, I made two red lines. Anytime body temperature is in there, that's the normal range, right? Body temperature changes a little bit during the day. So in the thermal neutral zone, let's just say it goes like this. Body temperature is in the normal zone. But watch what body temperature does if we get to the left. Is there any change? No, because you're still in the zone of survival. And if you go to the right of the upper critical temperature, look at that's homothermia, right? Homeostasis. You keep your body temperature constant in a range. But then it goes like this, death. But look what goes on the other end. Look what happens to body temperature. Why is it going up? It's not going up by metabolism. Why is the body temperature going up? The environmental temperature is taking, the body might be dead. But if you're in a sauna that's 150, and if you die, your body temperature is going to be 150 after a while, right? Or if you're stuck in a car seat, right? Your body temperature is going to tend to go towards the ambient temperature even if you're dead. So that's why body temperature goes up, but metabolism goes down, right? See that? Does that make sense, that whole range there? Artemis, she wants a second physical. You're gonna come this afternoon to another class. Let's see, you want to try this one too? I don't care. Here you go.
I don't care.
Okay. Okay, anybody have any questions? Okay, so now let me show you some data that we can write down numbers for lower critical temperature. And you'll have to see how it varies. You can even change the lower critical temperature of a sheet today by doing something to it. So let me show you that data. It happens to be on another page that I copied. Or no, I didn't. I tore out of the book. That's right. So now I need to focus here a little bit, or not focus, but zoom. Okay. Now these are numbers you're going to want to write down. So here it is. Lower critical temperature of a sheet. What's the parameters? It's a sheet that's got 5 millimeter fleece, so fleece length is not changing. But what we're changing is how much food the animal gets. And if the animal is fasting, fasting means we're not giving it any food. I had Aaron write down the degrees F because the chart comes in C. That's 88 degrees there, right, Aaron?
Yeah.
Okay. So fasting, the lower critical temperature of that sheet, they didn't tell us the age or the weight, but it's 88. Okay, maintenance means I'm going to feed it just enough to keep its weight constant. It's not going to gain weight or lose weight. So as soon as you start feeding, you're going to up metabolism, right? And look what happens to lower critical temperature. It's lower. Then, if you give it all you want, it's called full fed, or what's another name for that? Ad libitum, right? So ad libitum, it's 64. So there you can change the lower critical temperature of an animal by how you manage it, right there. Okay, so these are real numbers now, okay? And actually this book was written by a Purdue grad years ago, Stan Curtis. He's crossed over. And he was going to write another edition of this book, and he was going to send me chapters by email, and then he got sick, and that never happened. Okay, so now we've got a sheep that's being fed maintenance, so we're not changing maintenance, but look we're going to change its fleece length. How do you change a sheep's fleece length? You shear it, right? So let's start out by 100 millimeter length of fleece. The lower critical temperature is 27 degrees F. Then if you take fleece away, it goes to 48, 72, 82. That's quite a difference. And that could happen to a sheep today, right? You could shear it, and you change its lower critical temperature by your management technique. Okay. On another parameter, we got cattle. Now here it is, cattle that are fed to gain 0.8 kilograms a day versus 1.5. So what is that? 33. Oh, minus 33. Now look at that. That's degrees F. 33 degrees below zero, right? Minus 33. And the more they fed, that's minus 38. Okay, so here's one thing that I've never said yet. These values for LCT, there's one assumption. 0 miles per hour air velocity. These are in still conditions. As soon as you start with the wind, it changes everything. But so cattle are pretty hardy, right? Look at that. Look at minus 33 degrees. That's the left side of their comfort zone. Okay? So that's an actual value. Now, let's do a beef cow. I guess they've got maintenance. So now, think of this as, you can think of this as also the cattle with just no gain. So now you got minus 6. So if a cow's not gaining any weight, they have a significantly higher temperature. Higher temperature is, do you agree minus 6 is higher than 33? Minus 33? Remember when I say higher, the number is going lower, but it's a higher temperature, right? So if you get a test question like that, be careful. What does the higher temperature mean? It could be going from 33 to below 0 to 10 below. That's a higher temperature, right? 10 below is higher than 33. Okay. Dairy cow. Here we go. Now, if you're not familiar with dairy cattle, dry means not milking. It doesn't mean the coat is dry, not moisture. No, dry dairy cow means she's not milking, but she's pregnant, because that happens a lot. And the lower critical temperature is 12 degrees Fahrenheit. Then, if they're milking 2 gallons a day, which is, not very common, that's pretty low, but it ups your lower critical temperature to minus 11. So that's a lower temperature, right? And then if they're milking a lot, 8 gallons, and hopefully 8 gallons of milk, well, how many pounds is that about? It would be very close to 64, 64, right? 8 times 8, it's probably closer to 68 pounds, and there's cows that do more than that. But here it is, look at minus 40 degrees Fahrenheit. Wow. Remember last week I said a dairy cow is a walking furnace? Yeah. And you should notice minus 40 degrees Fahrenheit equals minus 40 degrees C. Because Aaron didn't make a mistake. If you calculate it out, minus 40 degrees C is minus 40 degrees F. Okay, so crazy. But if you look at those animals that have the lowest LCT, that means they're the first to get heat stress on the other end of the scale. The lower your LCT, the lower your LCT, the lower your UCT. And I don't think it shifts perfectly, but it shifts. Okay, some more data here. Swine. So then you've got a 2 kilogram hog, and if it's not gaining any weight, and it's just fed maintenance, it's 88 degrees Fahrenheit. So this is a little pig, because there's 2.5, no, was it 2. What is it? How many kilograms in a pound? 2.2, right? Yeah. So that's like only a 4 or 5 pound pig. So 88 degrees. So a baby pig, its LCT is 88 degrees Fahrenheit. Is that about the opposite to that cow above it? Pretty much opposite. And then if the pig is gaining a little weight, then its LCT goes lower, but not much. So this is pretty good data because it's hard to find this stuff. Then if you got a bigger pig, you can see the numbers go down. And then a bigger pig, the numbers go down. But feed is also a factor. So here, the bigger the pig, the lower the LCT. The more feed, the lower the LCT, right? For any given weight. And, oh, there's another, the bigger pig. Oh, okay, they've got a whole bunch of pigs here. Basically that. Chickens, we're not talking, I'm not sure what age these are, but 90 degrees Fahrenheit. Adult chicken, 64. And that's the end of the data. Anybody have any questions on that? So those are some actual numbers from a textbook that doesn't exist anymore. I don't think anybody could find it. Cut those pages out of Stan Curtis's book. Okay, well, then let's talk. I'm going to go now to my computer screen here. I'm going to reset my camera. Okay, so now I want to talk about what animals do to conserve heat or get rid of heat. And it's not behavior, but it's like internal things that happen. So, let me do a Google search here, and I want to look up a thing called the carotid reading. Whenever you see carotid, that's referring to the carotid artery. Okay? The carotid reading. And whenever you see Rete, R-E-T-E, that means a network of something. So, in fact, we know carotid is an artery, so then this is going to be a network of blood vessels that are involved with the carotid. And we'll go to some images. And this is going to be a little bit hard to understand, so that's why I'm going to explain it. I'm just looking for a good diagram. Okay, let me see if I can enlarge that a little bit. I'm going to see if... Okay, there we go. Okay, so this is a lateral view of, let's say, a sheep. And the sheep have a very functional carotid reading. Artemis does not. So it depends on what animal you're talking about. So sheep have a very functional carotid reading. So let me show you what's happening here. Here's the carotid artery. It's bringing hot blood from the body, right? The blood flow is here. When you get to this area, think of the artery as branching out many smaller arteries, okay? But then they come back together, and then they go up to the brain. Okay, so that's one thing. Now this blue is venous blood, and down here, did they label it jugular? Yeah, okay. This is the jugular vein. So blood flow is going this way, right? It can go this way, or it can go this way, or both. Would you agree that the blood coming out of this nasal region is going to be cool? Probably the coolest there is. Because when air flows through the nasal cavities, the heat from the nasal cavity wall is going to transfer to the cool air that the animal's breathing in, right? So by convection with the air movement, but conduction through the body wall. But look what this cooler blood, no, you can't have any more. Artemis. You've got two there already. Okay. You've got this cooler blood, but look, it can go two ways. And sometimes when there's two paths, you can change the path. What's that called when like blood can go two different ways and maybe one of the vessels constricts? It's an S word I'm looking for. Shunting. The blood can be shunted towards the carotid reading, or it can be shunted towards the jugular vein. Okay, so that's one case. So we got the cooler blood, and then look what happens to this cool blood. This blue, and this is hard to understand, and maybe I can draw it without the red there. That's a cavernous sinus. So let me draw that on the document cam. So what I want to do is I want to show you that there's a cavernous sinus that blood goes into. Sinus means a chamber full of something. In this case, it's going to be blood. So document cam. Here we go. So now what I want to do is, well, maybe let's see. Let's do the right over here. This is using this screen. Okay. So now what I want to do is I'm going to draw those nasal vessels. Right? The blood is here. And then right below the brain, what I want to do, look at the right screen. I want to draw this structure without the red. Okay, so now this structure right here is this area without the red. You guys see that? So this is a cavernous. N-O-U-S. Cavernous sinus. Full of venous blood. I haven't got the artery in there. So the blood coming back from the nasal cavity can go different ways, 2 different ways. But if you want to cool the brain off more than usual, then you would shunt the blood to this region, fill this whole cavernous sinus with venous blood. But going through that cavernous sinus is this area here with a lot of little arteries. Is there any mixing of blood? No. Is there transfer of heat? Yeah, the transfer of heat would be through the wall of this artery. It would go from the lumen of this artery into the cooler venous blood. Okay? And so what they did is, instead of having one vessel go through there, you make many, and you increase your surface area of conduction. Would you agree that the carotid reading functions because you have more surface area to transfer heat? Okay? And of course, then if I was going to draw the red, I could have the red come in here and then branch off, right? And then go that way. Okay, so that's the cavernous sinus, the carotid reading. Okay, so let's do another search. This time we're going to do, okay, I got a little dysfunction here. That's okay. Now I'm going to search for countercurrent heat exchange. Okay, what's that? I have no idea what's going on here. Okay, counter. Okay. I have lost my keyboard. I'm hitting the keyboard and it's not working. Okay. Well, okay, so let me go and see. Okay. Let me just go down to some of this stuff here. I'm not sure if my keyboard's working, but we can maybe get the same thing here. Okay. Come on. Well, okay, I don't think my keyboard's working right now, so let me talk about this and then we'll go on and see if I can come back to it. This is a reading assignment that talks about heat loss. And look at the 4 mechanisms they included, right? They're missing that one, but the one that they're missing is what? Condensation, not very important. If you read this thing, the take-home message is if you're in water versus air at the same temperature, and let's say the water is 40 degrees Fahrenheit, you will lose heat 25 times faster in the water than in the air. And all that comes down to is water is a better conductor than air. Okay? So if you fall into a lake that's 60 degrees or even 70, you can lose a lot of heat because of all that exposed skin, or your whole body is covered in water. Okay. Let me see if my keyboards come back. There we go. Countercurrent heat exchange. Okay. So the principle is, if you have two blood vessels where blood is flowing in opposite directions, you have a continuous change in the interface of temperature. And animals use this like in their legs or fins or whatever. So let me show you this one. Okay, so here's this diagram. Let me see if I can get a little larger. You have arterial blood coming from the body core. And it's 35 degrees C. And it's going to flow down to the extremity. As it flows down, it's facing venous blood, but through the body tissue. That's cooler. So heat, the arrow says where heat's going to go. Blood's flowing, but by conduction through the body wall, it's going to transfer to the other vessel. So you got 35, 30, 20, 10, but on the way over here, you always have heat transfer, because just by the numbers you would know how to draw the arrows, right? Heat always flows down its concentration gradient. If the number's higher and there's a number lower, then the arrow has to be towards the lower. You never can pump heat up. Okay? So that's called countercurrent heat exchange. So the carotid reading, the animal has no conscious control over it. Countercurrent heat exchange, the animal has no conscious control over it. Okay? And let's see. So there's other things. Let's see. Warm, cool. Here's a good example of a dog. Countercurrent heat exchange. Same thing, when you come down to the extremity, you've lost heat. And then so when the cooler venous blood is going back to the body core, you want it warmer. It'd be bad to send cool blood into the core. So this is a neat way to try to keep the core constant. Okay. Now, here's another thing about producing heat. Remember last week I talked about heat increment? And I remember now 2 more names. So what's heat increment? What's the definition of heat increment? Anybody remember?
The heat produced from eating.
The heat produced from eating. So I want to give you 2 more names for that. So let me type in heat increment and see what Google does for us. Okay, heat increment of feeding, which is the increased heat production following the consumption of food. Okay? So sometimes abbreviated HI, but that's a terrible abbreviation. So heat increment. Now, another name, the thermogenic effect of feeding. So that's the second name. Thermogenic effect of feeding. Okay? Heat producing because of eating, and it's the digestive processes. All the intestines are going to be working more. What type of muscle is in the wall of the small intestine? Smooth. And anytime muscle moves, heat is produced. Okay, and here now is probably the best name for this heat production. Let's see if I can spell it. Postprandial thermogenesis. So they got postprandial there. Thermal. Artemis, you like my cart, don't you? Yes, you do. Okay. So postprandial is a word that means after a meal. So postprandial thermogenesis is the heat produced, the rate at which heat is broken down, or food is broken down. Well, let's see, that's not the best definition, is it? Diet-induced thermogenesis, that's maybe another name. I guess there's not really a good definition there. Okay, here it is right there. Okay, in blue. Postprandial thermogenesis, heat production due to metabolism after a meal, temporarily increasing the metabolic rate. So when I lived in Minnesota and my dog was an outside dog, I fed him as late at night as I could. Why did I do that? So he could generate a little heat in the coldest part of the night. Okay? So if you're going to have some animal that you know is going to have a cooler time, I mean a dangerously cooler time, it's good to make sure their belly is full, basically. And that works with cattle too. When I lived in Nebraska, and it was going to be very cold and the cattle were out in the pasture, we made sure they were fed. Because the rumen makes a lot of heat. In fact, if you, and I might have said this before, if you measure the temperature of the rumen, deep down in the rumen, it's about 105 degrees. All the microbes generating heat. Okay, I think I'm going to stop there. Artemis is coming around, walking around. Startled. Yep. Don't let the dog out. Artemis. Hey, you. What are you doing? Artemis. You have that leash. Artemis. Artemis is what, 9 months old?
Yeah.
And just had a spay job?
Spay and gastropexy.
And prophylactic gastropexy.
Mm-hmm.
And then you're going to go bite people? Is that what you're going to do later? Okay, go bite people. Here she's got that treat from this morning. Artemis! Where's my puppy? Where's my puppy? Where's the puppy?
Oh my gosh.
Slippery. Where's the puppy?
Oh.
Whoa.
You don't have to worry about anyone being upset. Then they're going to use an ultrasonic scaler, which I have a picture of, but it's pretty much the same thing that your dentist uses on you. They use the little toothpaste thing and everything, so pretty much the same. Recovery, usually it's pretty much just for them to come out of the anesthetic, which is like about 30 minutes after, but the vet will